1991 at UNAM University with machine learning and also already going into the cosmology field. And then he was working still in Mexico and UNAM, also still in cosmology. And now for 1.5 years, he is doing a postdoc at the University of Geneva and has changed a bit the fields, now working Exoplanet.
Yep.
And today he will give his talk about this topic, machine learning for small data sets and the application in cosmology and also in Exoplanet. So, John.
Thank you for the presentation and for the invitation. Well, in this talk, I want to share with you some insights about how to deal with the small astrophysical datasets, and in particular with a few applications in cosmology and exoplanet detection. So first of all, in astrophysics, we have different sources, different types of data, high dimensionality of them, and also low samples. So we have expensive observations, and we need high precision for the physical problems and also for the measurements. So it's not the best scenario to have big amount of data. Always we can have simulations, but if we want to model the reality, we need to have real data that it's not always possible. So a brief overview about machine learning. In computational science, there is a field called computational intelligence that is based in computational methods for decision making and learning. For example, Bayesian inference, optimization algorithms, and all these kind of classical algorithms are part of this field. On the other hand, it is the artificial intelligence that are computational methods that try to mimic the human intellect. So, for example, in this field, there are also robotic or other fields that trying to mimic movements and thinking of the humans. And a subset that it's the one that we use in science is machine learning, that it's this subfield dedicated to the mathematical modeling of the data. And finally, there is a new emergent field called deep learning that is based in artificial neural networks, that is the most powerful tool of machine learning in recent years. So, okay, this is a neural network. It's not very impressive. So imagine that we have a small data set with 1, 2, 3, 4 columns, and we want to predict other 3 variables. So this is a very simple neural network with an input layer and an output layer, and we have connection between the input and the output. So to each connection between the nodes of this first layer and the second one, we assign a W, a weight, that is a parameter. So we can order all of these parameters in a matrix, and then multiply by the input. And then sum a small bias that it's like the displacement of straight rate, for example, and well, it's just to calibrate. And then we can perform this multiplication, multiply by an activation function, and then we have the output. So the goal is to find these parameters of this first matrix, and that's the goal. So for example, a larger neural network is like this. We have the parameters or weights that are these connections, are small numbers around 0. Initially, they start as random numbers, and with this matrix multiplication, we try to obtain y, that is the output. So we can think in the input like the independent variables and y as the dependent variable. At the end is like with any other model, we want to obtain y given x. that's the idea. The only difference with other models is that this model depends of all these W's here. So we have huge matrices, and to find these parameters is not something trivial. So we generate randomly numbers in this way, and we generate the first prediction. Then it can be very strange, very far of the target, but for that reason we need to measure this similarity between the prediction and the target. And we can use any kind of metric for that. The most simple and the most common is the mean square error. And the idea is to minimize this function like in other classical statistical algorithms to update the weights. So indeed, this was a very big problem in the 80s. For that reason, it was a called in artificial intelligence winter in the 80s, because to minimize, to optimize this way, it wasn't a feasible task. So until some people proposed these algorithms in conjunction, the gradient descent and the back propagation, then this task was solved, and also with the new power in the hardware, we can perform better models, and more with GPUs and TPUs that now are available. So the idea is to minimize this with these optimization algorithms iteratively until we have a good value for this error, and then we have the correct weights for our model. So this neural network works thanks to this property. There is a theorem called the universal approximation theorem that in general terms say that if we have a neural network with at least one hidden layer and a nonlinear activation function, we can model any nonlinear function if it's continuous. So this property is very powerful. This proves the existence of a neural network to model a nonlinear function, but the problem is that we don't know what is the architecture or the characteristics of this neural network. There are other types of neural network. For example, the previous one was under the supervised learning approach. There are other types of neural networks like the autoencoders that falls under the paradigm of the unsupervised learning. And instead to have independent variables in the input and dependent variables in the output, we want to have the same input as output. And that's because the goal of this kind of architecture is to learn the structure of the data. So in the middle of these neural networks, we have a compressed representation that it's an arbitrary dimensionality that we can choose beforehand. And then we can split these architectures in two to codify the input and to decodify the output. So in this first case of the classical autoencoder, if we use linear activation function, this is very similar to a principal component analysis, but thanks to the use of the nonlinear function, this can model more non-linearity. And more recent, there is this paper 1 decade ago, more or less, about improvement of this idea, in which some people suggest to take the advantage of this generation of random numbers and fitting to the loss function to, at the same time, sample the latent space. So in this case, in this first case, we don't have any idea about what is this compressed representation, but in this new approach, we can have at the end of the training also information about the probability distribution function of this latent space. And we can have a smoother approach. Indeed, this is the basis of all the generative models, for example, the diffusion models and transformers and ChatGPT use, for example, this kind of approach. Of course, much more complex, but that's the basic idea. And there are a lot of varieties of neural networks. This is an old chart, but even There is a lot with different kinds of layers. Some of them, for example, for images, we have instead to these nodes, we have kernels, and the parameters are slightly different, but the logic and the way in which these models are trained is quite similar. To minimizing the loss function, some of them are supervised or unsupervised, and the more new ones are generative. And we can use neural networks for any kind of data, for example, numerical, images, time series, text, and the layers are also different. Okay, this is a great theorem, but we have a problem. There is a called trade-off about the bias and the variance relationship, that is this first plot. So if we increase well, it happens with any other mathematical model. If we have more complexity in our models, we decrease the error between the target and the predictions, but we increase the variance. And if the opposite, if we have a very simple model, we increase the error of the predictions, but we decrease the variance. So the idea is to find a middle point that to avoid overfitting, that is the first scenario, and underfitting. For example, in this other part, we have a very basic example about these three scenarios. Underfitting is a model that cannot model very well the reality of the data. The overfitting case is one that is very well fitted in the extreme that we touch all the points. So it's very rigid, and it's not a good model because if we want to predict, for example, a point between this first one and this second one, we don't have a model that a prediction that is logical in the behavior of the data. So we need to find something like this, some appropriate model. And for that reason, in machine learning are very used these kind of plots. Our original data is split in 2 or 3 data sets, one for training, other for testing. So the idea is to fit the parameters of the neural network models with this portion of the data set, with the training data set, and to test with unseen data. Because in that way, we can prove that our model is working properly with data that it's not memorized by the model. So how to, sorry. So the underfitting is very easy to detect, because if we look the output and it's a straight line, or these lines here of the loss function are not decreasing with the iterations. So it's very easy to detect that our model is very simple. But the problem is the opposite case. With overfitting is not very well easy, because we have very small errors, and apparently can be a good model. So this is a big problem. How to prevent overfitting? The first option is augmenting the dataset. That it's not always possible in astrophysics, because the experiments are very expensive, and if we want to use just observational data, it's not easy always. So there are other options in machine learning in general. One is to select very well the complexity of the model, the use of regularization techniques, also validate and monitoring the training with some techniques like cross-validation and merely stopping, and also simplify the input space. If we reduce the dimensions of the input, it can help to predict overfitting. Also selecting very well the input variables. So for example, in this first case, we have some data from the growth rate on cosmology. These are these very few points that are the green ones with the big error bars. And in this case, we try to solve this very simple task using the redshift as input and predicting this observable and the statistical error. So, for example, in this slide, I want to show you how using the same architecture and just using different number of epochs or iterations, we have very different results. And the error is low in all the cases. So how we can know what is the best model? For example, I don't know if you have an idea or all of them are good because all of them have different physics. So it's very important to choose the correct one or one that it's good enough before to have a physical discussion about the modeling. So one technique to find these hyperparameters of the neural network, the most simple one is a grid. The hyperparameters are all these parameters that are fitted before the training, like for example, the number of nodes, the number of hidden layers, the number of epochs or iterations, the activation function, regularization methods, all of these should be decided before the training. And then we can choose several combinations of these hyperparameters in a grid, and then evaluate all of these combinations to find the one with the best performance. This is computationally expensive, but it's useful. For example, in this case, after using a very simple grid of hyperparameters, we obtain this model that is likely better than one of them. But even it can be not the best. And of course, all the time we need to verify the behavior of the loss function, that it's decreasing, that it's kind of converging to a very low value, and that the training set and the validation set have a similar behavior. Otherwise, we can have a problem with overfitting or underfitting. So another useful technique that we use in our work, dropout and Monte Carlo dropout. The dropout is very common in the deep learning pipeline. It's a regularization method that turn off randomly some fraction of the nodes of the layers in the way that in each iteration of the training, we have different neurons activated. And at the end, we have like a average of different models. And this is more robust, preventing overfitting. And in this more new work, some authors suggest to use this, but also for the predictions of a neural network. And in that way, we can have statistics of the predictions of the neural network, because we are turning off randomly some neurons during the inference, during the prediction, and then we can perform several predictions, calculate the mean, the standard deviation, and all the classical summary statistics that we know, and we can have some idea about the uncertainty of our method. So this is very helpful because this solves two tasks at the same time. It's a regularization method like the predecessor dropout, and at the same time we have some idea about the variance and the uncertainty of our trained model. So using this method, this first reconstruction is disorder that is smoother, and also we analyze the loss function. And of course, after that, we need to have in mind the goal of our model. For example, in this case, we are very limited to the range of the data. I mean, we cannot make extrapolations. We need to be very careful with that. The model is just learning the range of this. Also, we are only using this model like an interpolator. For example, very similar like a Gaussian process. And after this result, for example, in this case, the error bars of the reconstructions are the predicted error that I show you here, the predicted error from the data plus the uncertainty of the method. And using that, we can use a very similar analysis that with other non-parametric inference methods like Gaussian processes or histograms or other kind of non-parametric approach. And then we can compare the database model obtained by the neural network with theoretical predictions and start an analysis. But this analysis is by the hand to be sure that our training is correct, because otherwise we could have this kind of scenarios in which we have a big overfitting. So even with a few dozens of data points, we can have an acceptable model using optimization methods for the hyperparameters, using early stopping, uncertainty quantifications, and being very careful with the physical meaning of the outputs. And that's it. Okay, well, in this paper, we made other reconstruction with other observables, but just for have an example, I like this one. So we have different ways to make hyperparameter tuning. The first one is the grid. Also, we can use genetic algorithms that are optimization algorithms called metaheuristic because they don't use derivative. So you just generate an initial random points in a search space, and then using the same rules that in genetics, like crossover mutation and stuff like that, at the level of numerical codification, we can optimize a target function. And these algorithms also have a theorem that if we use the canonical genetic algorithm, we let it evolve with enough number of iterations, we always can find the global optima. So it's a very powerful property. We use properly these algorithms. And of course, there are other kinds of optimization algorithms and very good libraries like Optuna, in which are already implemented the grid search, the genetic algorithms, and other Bayesian methods to find the correct combination of hyperparameters. For example, in this paper, we explore the use of genetic algorithms in regression problems in cosmology. Yeah, we analyze different cases. I select one in which we are doing a regression of the distance modulus given the redshift. And for example, when we find the best architecture using a grid of hyperparameters and different configurations of genetic algorithms, we find that always the genetic algorithm find a best option, and also in a less number of evaluations. So it's a very good strategy. It's harder to implement, but it's very helpful. And always in this paper, we use just data sets of a few hundred or thousands of data points. Using this approach and all the techniques that I mentioned before, we can find very good statistical results, good modeling of these small data sets using genetic algorithms for finding the hyperparameter. So we applied all these methods in combination to combine traditional statistical methods with these techniques and different data points, for example, to model the distance modulus of LSST simulated data. And at the same time, we compare using this same simulated data with the best fit using Bayesian inference. And then we can compare the result of the theoretical predictions using this data with different direct energy models and the prediction of the neural network, considering the uncertainty of the method and the modeling of the errors of this simulated data. And also we try another work using the consumption curves, or also using a very few data points in the data set. But for that, another thing that I didn't mention before is that we need to use very small architectures to model the small data set. We cannot have a very huge number of layers and neurons if we want to model these tiny data sets. Also using regularization methods like early stopping, uncertainty quantifications, and analyzing very well that the output has physical sense, because otherwise we need to redo everything. Another application was more in the statistics part, but using data from cosmology, that it was to trying to speed up the Bayesian inference process, in particular an algorithm called nested sampling, that is very similar to a classical MCMC, but with the advantage that in each iteration we are calculating like a Riemann sum that allows to calculate at the end of the inference of the parameter estimation, the integral of the likelihood, and then we can have the information about the Bayesian evidence, that it's a very good variable to know what model is better in comparison. So we can make model comparison with this Bayesian evidence, and in nested sampling, at the beginning are sample n number of points, called light points, that are just a few hundreds or thousands. So we use these light points to train a neural network to limit this range of data in this parameter space, and to try to learn the likelihood with these samples. The idea is that sometimes in cosmology and in other astrophysical fields, we have very complex likelihood functions because are involved the different models, and also each observation that it uses in combination has its own likelihood. So we have very, very complex likelihoods that sometimes to solve derivatives or integrals are computationally very expensive. So we are using just these few data points to force the neural network to learn the likelihood, and then substitute the analytical likelihood evaluation with a training neural network that, as I mentioned before, is just a collection of matrix. So at the end, the likelihood is just a multiplication of several matrices. And in this case, for example, we found that it was necessary to start the training of the neural network near to the end of the Bayesian inference process, because otherwise we have a lot of variance. But even using this approach, using the Bayesian evidence like a threshold to start the training, we found that we speed up the Bayesian inference process until around 20%. So in this case, we use this data, cosmic chronometers, VO, supernovae, growth rate, and Planck, with 4,000 light points. It was the number of the data points in our training dataset. And well, this is the comparison between the posteriors obtained using the simulated likelihood by the neural network and the original one. So we have very good precision. Of course, using all the techniques and strategies that I mentioned before, we can achieve this. Now, in exoplanet detection, for example, this is a solar spectrum with a lot of wavelengths and the flux. So in this case, we have, sorry, I don't grow, no, well, around 300,000 of wavelength. And for this solar data, we just have 2,000 of observations. So we have high dimensionality and very few observations. So in this paper, it was proposed a simplification of this spectrum in this physical informed representation that it's a shell using the gradient of the flux with respect to the velocity. And in a previous paper, this representation using a principal component analysis was demonstrated that has enough physical information to detect and to be sensitive to the Doppler shift due planetary presence. So in this work, the neural network, it's a convolutional neural network trying to predict stellar indicators like the bisector, radial velocity, and the full width height maximum. In that case, to solve the problem of the small data set, it was using cross-validation, that it's a technique that randomly change the data points used in the training and the test data set. And it was very useful to avoid overfitting. Also, we use very simple architectures. We reduce the dimensionality of this very big spectra in this 9x9 matrix. And we use Bayesian optimization for the hyperparameters from the Optuna library. And in this way, we were able to have good models for this data. Now, in a work in progress, we are trying to add more physical information in this shell representation using different approaches, for example, using the temperature instead of flux, and with the same idea. Also using very simple architectures. Now we are incorporating the uncertainty quantification of the prediction with Monte Carlo dropout. And one small problem with the previous work was that using cross-validation at the end of the training, the neural network knows all the elements of the test data set. So it is working very well, but if we want to predict with using unseen data, it not works in absolute. So for that reason, we are splitting the test set and keep it stable of the training all the time. And then to the remaining data points, we increase the data instead to adding noise, that it's a classical technique in machine learning. You have data and you can increase your data adding noise. So in this case, if we add noise, we don't have the physical predictions that we want to find. So we are using planetary injections to increase the data set. So we use several combination of phases, periods, Doppler shift to increase this data. And then we have 10 times the size of, 10 or 20 times the size of the original data. And also we are using Bayesian optimization for the hyperparameters. And it seems working more or less well, detecting signals around 15 centimeters per second. The target is to find signals around 10 centimeters per second. That is the Doppler shift to planetary presence of a planet with the size of the Earth. Using an unsupervised approach, also a work in progress is to use this shell representation as input and also as output, and then compress even more in a two-dimensional latent space. And then in this new representation, we can analyze the latent space, that is this mapping here, and analyze the physics that is produced there. So to be sure about the the correct training of this variational autoencoder, we need to do all the things that I mentioned before, analyzing very well the behavior of the loss functions, analyzing the latent space that the samples have good sparsity, that are not concentrated in one point. And something interesting is that, for example, this is the plot of these 2 dimensions of the latent space using a variational autoencoder. We know the information about the probability distribution function of this latent space. And in comparison of this latent space, we can see the radial velocity, that is a variable that we can calculate using a cross correlation function, is this other plot. And in both figures, the blue points are spectra with a particular type of correction in the data. And the other one is the yellow with pink, are the data points without this correction. And we can see that in both cases, the behavior is very similar. So we can obtain similar modeling with this variational autoencoder, that it's a generative model, have probabilistic information of the latent space, and we are reproducing the physics that we obtain using classical methods. In this case, also, we are including physics in the inputs to reduce the large spectra with thousands of wavelengths. So also we are using simple architectures with a few of hidden layers with hundreds of neurons using regularization techniques like early stopping, and also Monte Carlo dropout to have an idea about the uncertainty of our methods and to have more robust predictions. Okay. Well, the conclusions is that small data sets demand to be very careful in the modeling of our machine learning models, in the design and the training. Overfitting is very risky all the time, and we need to avoid it to have confidence in our physical interpretations, in the discussion of our papers and presentations. So, the preprocessing must reflect the scientific goal. If we can combine variables in a way that we can extract more physical information is better. Also, we can remove some data points that we know that they are not expected to contribute in any way to the physical interpretation. On the other hand, as I mentioned several times in this talk, a careful hyperparameter tuning is very important, more in regression tasks, because I didn't show any classification tasks, but for example, in classification, we can have a wider range for a mistake. So, but in regression tasks, it's very important to be careful in all of this. Other thing is that we need to evaluate our models in both frameworks. In the machine learning framework, using the classical metrics, the mean square error, the loss function, and all the toolkit of machine learning, and also with techniques of the domain of relevance. If we have unexpected physical behaviors that contradicts the known physics, so we need to verify our machine learning training, or from the statistical point of view, also, for example, in our case, in the example of the acceleration of the Bayesian inference process, we wanted to be very careful with the meaning of the sampling of the posterior volume that it's calculated in each iteration, to be sure that we are not introducing noise or systematic errors in our machine learning training. And of course, finally, machine learning complements, not replace traditional statistical tools. It's a very powerful tool, but it's not a black box. We need to We can extract information if we use proper techniques like uncertainty quantification or generative models. So, of course, we have a lot of parameters, thousands of millions sometimes, but it's not a black box. So we cannot interpret individually each parameter, but we can extract useful information of this. And also it's machine learning, not machine learning. So that's all.
That's not magic.
Yeah.
Are there any questions for you?
Yeah, thanks for the talk. I was wondering which kind of neural network did you use for like approximating the line when you were.
Feed forward neural network.
But then, what is the output of your neural network?
The likelihood.
And how would you represent the likelihood? I mean, because I use like simulation-based inference, and then I mean, it's not like a normalizing flow or something.
No.
Like
No, it's just I didn't. Well, it's a neural network. The first one that I showed.
yeah, like a
Yeah. So, for example, the input are the free parameters. For example, if your model has 5 free parameters, you have 5 inputs, and the output is the likelihood.
And how do you represent that? I mean, we assume that the likelihood.
No, we know the likelihood because we to consolidate our training data set, we evaluate the likelihood several times during the classical Bayesian inference process. We save some amount of likelihood evaluations to train the neural network, but within the posterior volume that we need to learn in a specific.
So it's basically the likelihood.
Yeah.
Likelihood
Yeah. It's not like the likelihood free methods. Yeah. It's the analytical end. Just to speed up the evaluations of likelihood in case that we have involved integral derivatives and complex things. Thank you.
Just so I get it, because I also do kind of simulation based inferencing. So it's kind of like an interpolator. So you have So you have the life point and you use the likelihood of the life point and you interpolate so you can propose a new life points at the next step.
Yeah, indeed, but in this case it is a little bit more complex because the parameter space, we don't know the shape. So you can think that a point between 2 points is an interpolation and it can be outside of the volume that you want. So for that reason, we started training near to the end of the process because otherwise we have very strange results. Yeah, but at the end, it's an interpolation.
Another question is on the topic of predicting the cosmological parameters. Is that not like what do you gain from doing this in the form of neural networks as compared to Gaussian processes? Like because it looks like the canonical place where you want to.
Yeah, well, the only thing that I found is that in Gaussian process you assume Gaussianity in the data. So in this case you are not. So, yeah. Yeah, and also, for example, in these cases, the error is we are modeling the error of the observations, and we have just the uncertainty of the method. So, for example, maybe for some more classical Bayesian interpretations, Gaussian process have more Bayesian information. In this case, it's another kind of modeling, but then to reproduce the results that we obtain with Gaussian process is nice to see that.
Did you use any cross-validation during your hyperparameter search? And if you did, typically how long does it take to train your models in which kind of machines?
Well, for example, for this very small data set, computer, it is, well, my computer has an NVIDIA GPU with 6 gigabytes of RAM. But for example, for these other cases of data, we use the cluster because we have thousands of these representations, and we increase the data set with planetary injections. So it takes like, to find the hyperparameter, like 10 hours in the cluster, something like this. And
you use cross validation?
in this case, no. No, in these others, yes, but it was used to solve the problem of the overfitting in particular, not for but we can incorporate.
So when you use cross validation, how many folds?
You try several. It's like, for example, in clustering and all this kind of methods that you need to set the number of iterations. You try several and you analyze what is the best. So, yeah, it's trial and error. Yeah, but I don't use a lot of cross validation because when you are incorporating methods like Monte Carlo dropout, you are adding uncertainty, a Bayesian or a probabilistic nature in the training, so you can avoid the use of cross validation. In this work, it was not using the uncertainty quantification, so for that reason, it was used of the cross validation. Yeah, you can mix, but it's not necessary.
More questions? Anything? Something on the chat.
Yeah.
No.
No, we are like.
We have no more questions again. And then thanks, Isidro again. Well, yeah, we have still 10 minutes. I think. It's a wait for Isidro. We want to have some great people. And maybe Isidro also, Celsa will have a machine learning club later, 3 o'clock. Maybe might be interesting.
Okay, thank you.
We thought we launched a transformer.
Okay, nice, thanks.